Isolated system. So now you know delta E equals to dq minus d omega. In the case of isolated system, so we don't have any, we don't have any exchange between between the system and the outside medium. Okay, for example, we cannot change n, we cannot add q equals to 0. For example, we don't have, when I say energy transfer or transfer, I mean heat, okay, by heat. If the system is isolated, in this case, we have dq equals to O. Also, we don't have any work done on the system, because if we have, for example, we have a piston here. In the case of closed or open system, we have the P atm, atmosphere, which is equal to 1 atm equals to 10 power 5 Pascal, applied by the external medium. So this quantity of P is applied on the piston and is on the gas. In the case of isolated system, the system is closed. So we don't have any effect of the external medium on the gas, okay? In the case of isolated system. Here we have the piston, we have the container are isolated, okay? But you can have the gas is isolated only. So in this case you have P. But if I take all the system is isolated, so we don't have P atm. So as we don't have any force applied from the external medium, in this case we don't have any work done on the system from the external medium. So d omega external equals to O. In this case, Q equals to omega equals to O. We don't have Q, we don't have omega, so delta E equals to O. So E final equal minus E initial equals to O, E final equals to E initial. So you have to know, in the case of isolated system, E is constant, okay? Cyclic processes. What I mean by cycle, we have a cycle. First of all, in the case of cycle, I mean you have an exchange of energy with the external medium, okay? For example, we have a quantity of water, and I can give a heat to the system. For example, it's closed, and here I give Q. So we have Q hot. Or I release a quantity of heat, we have Q cold. So we have an exchange of energy between the medium, between the gas and the external medium. We have Q positive and Q negative. For any cycle, we must have Q cold and Q hot, okay? So here you have to know we have Q hot, and also we must have Q cold. It's impossible, you cannot give quantity of heat and you don't lose a quantity of heat. If you give Q hot, you must have Q cold, okay? Okay, second point, in the case of cycle, we start by the point and we have to finish by the same point. Okay, for example, if I start by the point 1, I go to 2, 3, 4, 1. I come back to the same point. Okay, this is a cycle. Or, okay, here we have P constant, V constant, P constant, V constant. Here also, for example, we can have A, we have A to B, B to C, C to A. Okay, we come back to the same point. Here it can be T constant between A and B. Between B and C, we have V constant. Between C and A, we have P constant. And the same for the last point. Okay, we start by the point A, by the point 1 to 2, 3, 4, 1. This process is not isolated. Simply. Why? Because you have Q hot and Q cold. Anytime you have Q hot and Q cold, the system is not isolated. We have an exchange of heat. In the PV diagram, the cycle process appears as a closed curve. As you know, we have a closed curve. It's not open. The internal energy must be zero. Okay, it's a very important point. For example, here we have a cycle. One, we can say delta E of the cycle, of the total cycle, equals to delta E 1, 2 plus delta E 2, 3 plus delta E 3, 4 plus delta E for 1. You have to do the summation of all the internal of all the exchange of internal energy. Delta E of the cycle, the total one, equals to 0. Okay, for any closed cycle, for any cycle. Also here, delta E of the cycle equals to O, equals to delta E AB plus delta E BC plus delta E CA. And here also delta E of the cycle equals to O. Okay? Energy Q added equals to the work omega done by the system. You know, we have delta E equals to delta Q minus d omega. Okay? Of the cycle. Of the cycle. Of the cycle. We can apply this relation for one cycle, and you can apply also for one process between 1 and 2, or for one cycle. As delta E of the cycle equals to O, in this case, delta Q equals to delta omega. Okay, so delta Q of the cycle equals to d omega of the cycle. Okay, you have to know this relation in the case of cycle. The last point, in a cyclic process like this one or any one here, in the case of a closed curve, the network delta omega, or you can say omega of the cycle, equals to the area inside the closed curve. I mean, equal to this one. Okay, this one, the area of this one, equals to omega of the cycle. Okay, and this one is omega of the cycle. This one also. Okay, equals to the area. Okay, if we have only one curve like before, for example, I take P constant, only one process, in this case equals the area under the curve. Okay, we have a difference between the closed cycle, between a cycle and between one transformation. I give you here an example. Application of the first law of thermodynamics. You know here we have a gas inside the piston. The gas absorbs 400 joule of heat. What I mean? I mean Q hot. When the system gain a quantity of heat, it means Q is positive. When the system lost a quantity of heat, so Q is cold. So Q hot equals to plus 400 joule. And at the same time, does, okay, the gas, okay, the gas does 120 joule of work on the piston. Okay, when I say the gas does this quantity of work, so is the energy done by the gas. Okay, the energy done by the gas. Look here, when we have Qn applied to the gas, I add this quantity. In this case, the volume will increase. Okay, P of the gas increases, and the gas will push the piston up. Okay, so as the volume increases, you know, if we have an expansion of volume, in this case we have omega must be positive. Okay, I am talking about omega pi, so equals to 120 joule. If I tell you I have 120 joule and we have a decreasing of volume, so you have to say omega equals to minus 120 joule. Okay, in the case of expansion, you put plus 120. In the case of compression, of decrease of volume, you have to put omega equals to minus 120 joule. We have omega, we have Q. What is the change in internal energy of the system? Okay, so as we provide the gas, the work by the gas, you know, if we have an expansion, you can say the work provided or released, okay, by the gas. Okay, you can, or by the gas. In this case, omega is positive. Okay, equals to 120 joule. I want to calculate delta E. Delta E equals to dq equal to 400 minus 120 joule. We get finally, I can solve it. So here we have delta E equals to Q minus omega. The final value delta E equals to 220 joule. So as delta E is positive, in this case we have an increasing of the internal energy. We can say we have an increasing of the temperature inside the gas. Okay, simply you can apply directly the first law of thermodynamics. You know, we have a conservation of energy. Q hat added to the system, we have 120 joule consumed as work plus 280 joule consumed as internal energy. So the energy added to the system equal to the energy consumed by the system between, uh, you know, delta E equals to delta Q minus d omega. So dq equals to d omega plus dE. Okay, the summation of the energy consumed by the work and the energy consumed by the internal energy. Okay. Here, in general, I want to study four processes. I want to study the case of P constant, in the case of T constant, in the case of T constant, P, V, T, and Q. Okay, if we don't have any heat added to the system. First of all, isochoric process. What I mean we go from the initial state to the final state with the same volume. V initial equals to V for, final. Okay. I will talk in details each one, but in general, we don't have a change of volume if we don't, and omega equals to integral PdV as delta V equals to O, so omega equals to O. Isobaric process, we have P constant between the initial state and the final state, delta P equals to O. Isothermal process, in this case, we have delta T equals to O. You know, delta E depends only on delta T. If we don't have a change of T, so we don't have a change of E, okay? In the case of isothermal, in this case, we have T initial equals to T final. So T final minus T initial equals to O, and delta E equals to O. Okay, in this case, E initial equals to E final, and T initial equals to T final. Okay. Adiabatic process, what I mean, delta Q equals to O. We don't add, we don't release any quantity of heat from the system. For each case, I want to study the curve, the path between the initial state and the final state. What is the shape? We can calculate Q for each step. If we increase the volume, if we decrease the volume. For example, if we have P constant, at P constant, we can increase the volume or decrease the volume. If we have V constant, also we can increase P, we can decrease P. At T constant, we can, okay, anytime we can manipulate the system. It depends to the situation, or depending on the situation. Before starting with the processes of thermodynamics, let me define one parameter. You know, we talked about the heat capacity C equals to Q divided by delta T. We talked about the specific heat, small c, equals to capital C divided by M, or delta M. Okay, small c, no, equals to capital C divided by M, or, okay, this one is heat capacity and this one is specific heat. And we calculated in general Q equals to mc delta T. Okay, the quantity of heat added or released from the system, the mass of the system, the specific heat of any gas, of any object, times the change of T. Here I want to talk about the molar specific heat capacity. You have to know the molar specific heat capacity. I mean capital C times P. Okay, at P constant, in general it's Cp or Cv. Okay, the name is molar specific heat at P constant, or molar specific heat capacity at V constant. So if we have P constant, Cp equals to the molar mass capital M times the heat capacity small c, or not heat capacity, specific heat. And at V constant, the molar specific heat Cv equals to the molar mass capital M times the specific heat small c. Okay. In this case, we can say M times small c, it's here, small c equals to Q divided by M delta T. Okay, we can say equals to M times small c Q divided by M delta T. And M divided by N, the molar mass divided by the mass equals to N mole. So we can say here Cp or Cv equals to Q no, here equals to M divided by capital M. Okay, N equals to M divided by capital M. Okay, let me. So if we put here M, capital M equals to N divided by the mass M. Okay, so here we have, let me write again the relation here. We can write Cp or Cv equals to M N here M equals to M divided by N. Okay, so we can write M divided by N times Q divided by M delta T. So M with M, finally we get Cp equals to Q divided by N delta T, or Cv equals Q divided by N delta T. Okay, so Q equals to N Cp delta T in the case of P constant isobaric process, and Q equals to N Cv delta T in the case of the isochoric process. Okay, so finally you have to know the relation Q equals to Mc delta T. Mc delta T, C is the specific heat, capital Q equals to N Cp delta T in terms of N, and Q equals to N Cv delta T. In the case of P constant, we use this one. In the case of V constant, we use this one. Okay, you have to know only these relations. Q equals to Mc delta T, equals to NCP delta T equals to NCV delta T. Okay. So this is a general case, CP and CV, and when Q equals to NCV delta T and Q equals to NCP delta T. Let's go now to the isochoric process. Before, you have to know, in any case, in the case of P constant, V constant, T constant, Q equals to O, I mean in the case of the isobaric, isochoric, isothermal, and adiabatic, in any case, delta E equals to NCV delta T. Okay? In all the cases, you can write directly delta E equals to NCV delta T. Okay? Okay, we do some application later to understand very well, but you have to know this notation. Delta E equals to NCV delta T in the case of V constant, in the case of P constant, in the case of T constant, or Q equals to O. You can use this notation. Okay, and as you see here, delta E is direct proportional to delta T. Any change of delta T, you can get a changement of delta E. Delta T equals to O, so delta E equals to O. Okay,